But the good thing that came to Fifth Civil Court, their justice was served. All the people of the Sorry, I'm not
So let's continue this
Yes.
conversation.
Are we ready? Hello, everyone. Welcome to the second tutorial in this room and the time slot in which the third and the fourth tutorial take place of this IETF 103 in Bangkok. Welcome, everyone, to Bangkok. I am Niels. Don't be afraid. I won't be giving the tutorial, but I'm a member of the Edu team. And with the Edu team, we're trying to help newcomers and everyone in the IETF get to know other parts of the IETF and have it be a nice experience for everyone. So we do this tutorial, these tutorials every time, and we want them to make it as useful as possible for you. So we will be sending on the attendees list a survey. So if you could please fill it in and tell us what you thought about the presentation that's coming up, but also feel free to email us with suggestions for tutorials that you really would want to see. So you say, I would like this technology explained, or an overview of implementations of Quick, or just tell us what you want to see and we'll get on it right away. Now, I won't take much more of your time, but if you have questions and stuff, feel free to approach me or other people of the Education Directorate in the hallways, or find us on the Edu Team Wiki, which you can find in the data tracker. And now, without further ado, an introduction to the internet area by Pascal Chibier. Pascal, who is pronouncing his surname much better than I do.
Sorry.
Okay. Thank you, Niels. Is it correct? Okay. How many of you are newcomers to the IETF? Is it your first time? Please raise hands, just for me to figure. Okay, half the room maybe. So a good number of you have been here before. If you don't know this application, there is a nice application for your phone, the IETF application. With this, you can schedule your meetings, select when you're going to meet, attend which meeting. And you will find that right after this talk, there is a newcomers quick connection, and it will be in Garden at Queen's Park. So a lot of people from many areas will be there and ready to answer your questions. That's actually where we meet and greet and welcome new people. And so if you have any question about one of the working groups I will be talking about, or Suresh will be talking about, then please attend. Again, it's in Queen's Park, Garden at Queen's Park. So it's going to be nice. Usually there's food and drinks, right? So at least one good reason to come. And yes, we will answer any of your questions. With this, here is the program for today, and maybe I will sit here so I can read something. Usually there is a pink square somewhere because there's a camera, and you need to stand if you speak near the inside the pink square, so get used to that. So first thing I'm going to do is for the newcomers, really position the IETF versus other SDOs and how we operate, because not all the standard defining organizations operate the same way. So once we pass that, we'll take a closer look at the IETF itself, how it's split into organization areas, ISG, and then we go deeper into the working groups within our internet area. I have made a selection. It's just my selection, right? It's not the best working group or whatever, but I've made a selection of working groups that I want to highlight before we deep dive into each of them. And that's because I use them to illustrate that not all the working groups function exactly the same way. They don't all have to deal with the same kind of problems. And so every working group may have a distinct and interesting crowd. So depending on what your interests are, well, we'll go through that and you'll see. Then yes, we have the more exhaustive list of all the working groups and what they deal with. And I hope we don't spend too much time on that, because you can find it on the web, etc. And then we'll go through the important links, and you'll see that the IETF website is really well built and easy to follow. So I'll show you through that. And then questions, etc. So the first thing I wanted to show is that I've been participating to a number of those guys, and I realized they don't operate the same way at all. So there is a category that we call open standards, usually like IETF and IEEE, and in those kind of standard organizations, people can come as themselves and they can talk as they want. There is in the IEEE they still need to announce what their affiliation is, like I work for Cisco, but still it is a personal representation. You speak for yourself, and it's not backed by countries or by political organization or geographical organization. It's mostly backed by companies, which are worldwide. I take that as a difference between an organization like ETSI and ITUT. ITUT is really led by governments. I mean, the governments send people to the meetings, and the local interests are being served here. ETSI serves mostly the European zone with 3GPP, etc., even if some of the standards can be spread larger. So the second type of category has more regional and I would say state interest, whereas IETF and IEEE have more global and I would say corporate interest. And then there is a third category, which is more like alliance, like the Wi-Fi Alliance, ODVA Avenue. ODVA is for industrial, Avenue is for audio video, you all know Wi-Fi. Those alliances are more usually vertical. Wi-Fi is a bit different, but ODVA Avenue, they really serve the interest of a particular vertical, industrial, audio video. And so you will find, again, corporations mostly, it's not by state, but it's really focused for a particular class of business. So with the IETF kind of provide components, and IEEE provide components that can be integrated in standards that those guys build. They will build the full stack, they will end up with devices which can incorporate and serve a particular class of probe. And for doing that, they will actually use building blocks that we have designed at the IETF and IEEE. Okay, and this was supposed to be an animation. Yes, so that's maybe I should have used my. Okay, so here are the, if you don't know the PowerPoint, then you will see the animation. But the bottom line is the areas at the IETF kind of resemble the usual stack. That we have defined this 5-layer stack with the physical link layer, IP layer, transport, and application. And you find kind of the stack represented for the layer 3, 4, 5 at the IETF with the ART, which is application and real time, transport, which is layer 4, and internet area, which mostly serves layer 3. And then you have other areas which are more vertical. For instance, management. You need to manage all layers, and security. So in the security area, you will find the definition of a number of well-known protocols, and I just picked as an example TLS. And I guess people have heard about TLS. That's defined at the IETF in the security area. In the management, we define now netconf, for instance, YANG, all this YANG standard, which is kind of replacing SNMP. Because so SNMP basically, and you have operations as well. So we have operation and management, and I listed V6 because I will mention it later. So V6 is where all the feedback for deploying IPv6 comes, and so the best practices, etc., can be developed within this area. Application real time, that's where core, for instance, for the IoT, but HTTP, which is the HTTP beast now, we are working on the next generation of HTTP. Transport, so your use of TCP, obviously, it came from here. Now we are working on MPTCP, multipath TCP, so you can have multiple paths being used in parallel for a TCP session. And there is also this new effort, Quick, which allows you to build sessions over UDP. It's supposed to be very fast, so we'll see what Quick comes up with. And then we have the internet area here, which mostly serves layer 3. So that's where Sixman, for instance, is defining IPv6. And DNSSD, which is how we can do DNS across the layer 2 boundary. And last but not least, we've got the routing area, which I kind of positioned at layer 3. This is where all the routing protocols are being designed. That's where BGP was designed, OSPF was designed. And now we have LSR, which is kind of merging the efforts on ISIS and OSPF. But those protocols are still alive. And then there is also, I listed Spring, which is a kind of a recent effort for doing source routing. We call it segment routing. That's how you can reroute some flows through different paths to make sure that you don't, for instance, you go around the prime or you don't create a congestion in the middle of your network. Okay, so these are the main areas of the IETF. And in my slides kind of hidden, you can see the number of working groups. They don't have the same number of working groups. Actually, ART is the biggest one. They have 29 working groups. And that's why they have 3 area directors. INTA is kind of big, but we still have only 2 ADs. So you're kind of the most loaded ADs. That is worth, I think, in routing, they have more than 20, they have 3 ADs. The most loaded might be management. No, I don't. Well, we're second best, something like that. You're very loaded. That's what it means. And then we have this area here, but it's more like a management tool, right? We have 2 working groups. That's how we prepare for the meeting, etc. So it's kind of, this one is very special. That's why I put it on the side. So diving down the internet area. So like as I said, we are looking at the IP layer technologies, all the fundamental protocols, IPv4, IPv6, DNS, DHCP, the base of ICMP, all the basic building blocks that you know about in the IP stack are defined in the internet area. Same goes for mobile IP, DMM, distributed mobility, HIP, I will mention it. It's a separation of the locator and identifier within an IP address. Today, you say where and you say who in the same IP address. It tends to separate them. Then we also try to make management easier for home networks. That's why we have this special working group. And I will mention why I find it particularly interesting. So I'll come back to HomeNet, defining how you make a network at home, like multi-subnet home network. Then we've got all the evolution of IPv4 and IPv6. So it's mostly 6-man, but you also have SoftWire, which allows you to build tunnels for V4 over V6 or V6 over V4. You've got all the IoT at layer 3. So that's where what we call IP over foo. What we mean by IP over foo is, you've got this collection of different link layers for instance, for IoT networks. Well, they are the foo in the IP over foo. So you have IP over, I don't know, Bluetooth Low Energy. You have IP over 802.15 for IP over foo. And 6LoW and LP1 are the places where those foos, the IP over foos, are being defined. And then finally, the INTA area is where the work on time is happening. And you will see that's my conviction over time. The network will be your source of time. As you connect to a network, we don't do it yet fully, but soon enough, when you connect to the network, before you do anything, you already get a sense of time. That's how we're going to make the network deterministic. That's how we are going to simplify the routing protocols, because if we had a sense of time, a lot of things in routing would be a lot easier. So TikTok and network time protocol are related to time, and they are in the INTA area. I expect that to grow. Time will become more and more important at layer 2 and at layer 3. So here I give a more complete list, so you'll have to go through the slide, but also that's easy to find on the IETF data tracker. So there is the full list of the working groups. And we'll be going through them, see what they do. But first, like I said, I will give you an overview of selected 4 and why I selected them, just to illustrate the kind of work that's taking place in the INTA area. So the first one, it's kind of the king of working groups, kind of, because that's where IPv6 is being defined. That's 6-man. So it used to be called IPv6, but now it's 6-man because it's supposed to be maintenance. Okay, so maintenance saying, V6 was defined. Let's tune it, let's fix it, but not change it too much. That's kind of the idea behind maintenance. Actually, the biggest thing that has happened in 6-man is the publication of RFC 6200, which is the the internet standard version of IPv6. So you'll find that we have degrees of standardization at the IETF, and the highest degree, when we are really sure here is the standards, everything is quote unquote perfect in it, that's when we reach the level of internet standards. And we don't have many internet standards. IPv6 became, like last year or the year before, became an internet standard last year, became an internet standard with 6200. Because it is a fundamental tool, people are very sensitive to the evolution of IPv6. So 6man has this quote unquote political dimension in it, where some people will say, hey, you can't change the protocol. People are deploying it. They don't want they want to feel the protocol they're deploying is stable. We really need to be conservative about what we do at 6man. And other people will say, hey, if you don't evolve, you die. The world is changing. IPv6 was initially designed in 98. It has to evolve with the world so as to still be aligned. So those two forces will be fighting at 6man, and that's a very interesting tension and very fruitful. Sometimes one side wins, some other times the other side wins. And I have examples of where the evolution is happening, for instance, segment routing that I was discussing earlier, which will have to change the way IPv6 works. In 6200, there was also this discussion about headers. Sorry? 80, I will say 62, 8200. Sorry. So yes, we are in 8 now. So in IPv6 now, you will see that, for instance, the hop by hop header is rewarded. It's not a strong standard that it used to be. You can ignore it now if you're a router in the middle of the internet. So things have evolved compared to the earlier 2460. So that's the political dimension, and I think it's kind of unique to this working group, and it creates a very interesting tension. Another aspect which is kind of unique to 6man and spreads on the other groups which use IPv6 is all this, I would say, sociological, for the lack of a better word. We have to care about how the society uses the IPv6 addresses, and there are at least two angles which are very important. The first is privacy. If you keep using the same IP address, then people can track you on the internet. So we want addresses that don't allow people to track you if you don't want to be tracked as you're going. So this creates a whole set of new requirements to IPv6, and 6man has been dealing with that. Another tension, which is kind of interesting, is the tension between, I would say, a hippie user who wants to be able to form any address he likes in any network, and I would say the corporate administrator, network admin, who wants to see who's logged where with which address. And so there is always this tension between the IPv6 desire of total freedom and the corporate desire of knowing what's going on in my network. So this also has impact on the definition of the protocol. And finally, there used to be this group called Savvy. Now it's disbanded, but kind of 6man now will have to do the maintenance for it. It means source address validation. It means, oh, if somebody has a certain address, can somebody else use that address, steal it from him? Hey, supposedly not, but with the base IPv6 protocol, it was kind of hippie. Everybody can use everybody else's stuff. Now we want to actually protect. We want the network to ensure that if somebody forms an address, okay, he may be free to form that address, but when it's done, it's his address. Nobody else can come and intercept the packets. And the other way around, if you want to use an address and it's not topologically correct, you should not be allowed to do that. Okay, so it's more a matter of police now. So we're doing politics, we are doing sociology, and we are doing police. And it's all those aspects actually change the protocol. There are a number of RFCs which are still happening about how you control IPv6 without changing the basic header or anything. We are really changing the way it can be used in the world. So that's 6man. I mentioned 6ops. 6ops is not in the INTA area. I told you it's in the ops and management, but it's still very interesting because it's the counterpart. It's the feedback loop to 6man. That's the real world coming back at IPv6 and say, okay, here is how it's deployed. This works, this doesn't work. This should be changed, etc. So V6ops is the place where this discussion happened. And usually they have 2 meetings at each IETF because it's a very, very active working group. Then there are the IoT working group of the INTA area. So I picked two, there are more, but I picked those two because they are the IP over foo. As I said before, another aspect of what's happening here is since we are layer 3, there are layer 2s. And now we are the working group, which the area, which is facing the layer 2s. And there are many of them, mostly with the IoT. There are tons of various radios that have different property, the way you do IPv6 over them, the way you form addresses, for instance, the way you encrypt you encode the packet for compression. All this varies with the foos. So initially, it was IPv6 over Ethernet, down. Wi-Fi is Ethernet, down. Okay, Wi-Fi is not Ethernet. That's one thing, and it appears now. As the network gets bigger, etc., the difference between Wi-Fi and Ethernet appears to the point that we may have to look at IPv6, how it works on Wi-Fi. And then all those other networks, I just listed a number of them. It's not even a complete list. So you see, so Bluetooth Low Energy, BACnet, which is for buildings, near field, power line, so using the volt wires, Z-Wave, it's a radio for like lighting, 802.15.4, that's the radio used by Zigbee, by Thread, by 6-dish actually. LoRaWAN, LoRa, it's a wide area network, low power wide area. So it's a few bits per second, kind of. Sigfox in the same family. NB-IoT is a bit more powerful, but it's still in the low power wide area networks. So those are the working groups where all those things happen, meaning that the crowd in the room will be different. You will have a lot of people who specialize on their radios, people who have never heard about IP in the first place. And we pull them in so that they get interested in the IETF. And we come back with solutions that they can use across those technologies so they are interested in using them. For instance, LP1 is defining a compression and a fragmentation which can be used in all three. But at the moment, I was a meeting, LoRa Alliance meeting in Tokyo, like last week, and they were discussing about using our fragmentation for LoRa. The IoT is also bringing new use cases, new shape of traffic to the interior. For instance, if you're doing sensor network, AMR is metering, your electrical meter. This is an unusual traffic in that it's mostly coming from the meters all the way to the application, but not much the other way. And when it's going the other way, it has a very special shape, like you have to reflash the device. So this creates an imbalance in what's going on. And that can be leveraged to improve the compression of the protocol, for instance, if you know what kind of traffic goes through, or how you allocate your bandwidth in your network. As we go, we realize that some basic operations of like IPv6 neighbor discovery is not appropriate. A neighbor discovery uses broadcasts always through. It's using a lot of broadcasts. When you have a low power radio, it's a mesh. You don't want to broadcast a mesh each time you're looking for a meter. So you have to redefine, and we are doing it, redefining IPv6 neighbor discovery, which is really a core building block of IPv6 if you look at it. And there are two big building blocks. One is addressing how you form addresses, and the other one is neighbor discovery, how you find your neighbors. Well, we are redefining a new variation of neighbor discovery, which is more like a Wi-Fi association. You have to declare yourself to the network to get your packets back. So there is never a broadcast. And as I said, the key operations that you have to do in a IPv6 over foo is if it's a small MTU, the frame size is too small for the IPv6 min MTU, then you have to define the fragmentation. And then either compression, addressing, how you form addresses, e.g. based on MAC address or not, etc., privacy. All those discussions happen again and again for all those over foo. And then there is 6-dish, and it is kind of special to me, just like Omnet is kind of special, in that we are not trying in this working group to build like small components that will be used in a bigger picture, like remember my protocols on the right, my alliances. In 6-dish, we are already trying to build a meta RFC, an RFC of RFCs, because there are like more than 8,000 RFCs in the IETF, and those alliances, usually they're composed of people who never came to the IETF. And they want to build a new IoT type of network for industrial. And they look at it and say, ooh, out of those 8,000 RFCs, what should I do? Which one should I take? And there is a consortium which tried, was called Zigbee IP. They wanted to do Zigbee for electrical, for your electrical meters. And so they came to the IETF many times, and they ended up building this stack based on RFCs from the INTA area, RFCs from the routing area, RFCs from the ops area. And they tried to put that together. It was an immense effort. It didn't work very well. Because we realized as we did that those components that we produced in the various areas did not really fit together. So the effort in 6-ish, was defined for a particular 822.15 for Mac, but really most of the work happens at layer 3. We are in the INT area. And the question was really, how can I build a solution, like a big RFC of RFCs, so that all those alliances that I was talking about could adopt IETF protocols more readily. And there are really 3 things that we did in this working group. One of them was to define architecture, which says, okay, this protocol is here, it connects with that. If the flows are redundant, here is which one you pick. For instance, the routing protocol could be something that ND is also doing, which one? And build that solution, propose it. And at the same time, we were finding gaps. And 6-ish has been pushing work in 6-low, in raw, so that at the end of the story, the picture is complete. The gaps are filled, and the overlaps, well, a selection is made on which of the overlapping technologies being used for a particular case. So this is what happened at the IETF. At the same time, we had open source activities, and we have 2 open source stacks which kind of which are built on this architecture, and we interrupt them as a 3rd component. So we have Etsy actually helping us doing all the interrupt tests. So we have a real Etsy structure for doing interrupt. We have open source code, and we have the IETF Meta RFC. And with that, we prepare this special bundle. So you see, it's not a classical working group building several RFCs. It's more like, how do I make all those RFCs work together for IoT purposes? So it's kind of interesting. HomeNet is a bit like that. They are building a home network. Here we are building an IoT network. So how should my home network operate so that my grandma can have a subnetted network and she doesn't understand anything about network? It has to be all automated. So that's why HomeNet is so interesting as well. Each time we still have to define a few RFCs because there are holes which don't belong to other working groups. So we have to take them home. But you'll see that most of the work is actually to study how that works and providing the big picture that actually works. And do you want me to do it? Do you want to do it? Okay. Little pause. This is the time for the drink and for the deeper dive into all those working groups. I'm just out of my plane. I didn't have a chance to go to my room yet. So there we go. So we have like, I said 16 working groups in the interior right now. So we'll go through the 16, okay? But just to give you an idea of what they do. But you had the big picture already, so we'll go at an angle. So this is how actually several years ago Suresh sorted them. The sort has not changed much, just some working groups have gone, some new are formed. But because working groups come and go. As it goes, I didn't mention it, but the areas are kind of stable. They used to be very unstable. We used to have new areas and then disband them and form new areas. But over the course of the 10, 15 years, the areas at the IETF have been very, very stable. But the working groups inside the area change a lot. I mean, a working group lasts like 4 years, maybe 5. Some last more, like 6 men. But usually they come and go, depending on the needs of the day. So we have those related to time, which is kind of a very special sort. We have those related to IoT. So low power is a classification. We also say constraint because sometimes most time the power is the constraints, not always the case. It can be memory, it can be CPU, but usually it's power. Now, we used to have more transition working groups. Now we just have software, which really belongs to there, but I kind of put 6 men in there too, because that's everything which has been done for IPv6 and which is complete kind of ends up being maintained by 6 men. And we'll go through all the other. Interior is a bit special. You'll find that each area has its own working group for general purpose. Everything that fits to the area but not to an existing working group can be proposed to the interior. So we do RFCs in the interior as well. We've got mobility related, look, everything which derives from mobile IP. I placed IP wave there, which is IP for vehicles. They are not doing mobile IP, but I did not know where to put it. It's not really low power. It's kind of related to mobility and related to low power. But saying that a car is low power is a bit an exaggeration, so I place it here. And there is another angle that Suraj put together, and I really like. You see kind of the evolution, the working groups which just appeared. The most recent one are those two, IP wave and low power wide area networks. And recent are DNS-SD, so it's DNS across a larger network. DNS Bonjour-like across a larger network beyond the subnet. And then you see mobility management. 6man, I place it straight in the middle, it's here to stay. And then you've got others like this one related to IoT. We'll go through all that. But you see, normally the working group are injected here and they go out here. And now let's start. So 6low. So basically, you've got this helper for every working group. So it's just a matter of giving you a hint of what the working group does and what it's about. So 6low is the new version of 6LowPan. Have you heard about 6LowPan, raise hand? A bit, not much. So 6LowPan is how you do IPv6 over constrained networks like 802.15.4 initially. LowPan itself, without the 6, is the denomination by IEEE of 802.15.4. So it was really initially IPv6 over 802.15.4. So we delivered 6LowPan neighbor discovery, which is the first attempt at doing this registration, this pseudo association at layer 3 that I was talking about. So 6LowPan terminated, went through the picture like we said before, and it was replaced by 6Low. And you see that the difference is that the WPAN went away. So the concept of being focused on 802.15.4 is gone. Now 6Low handles all variety of class of, I would say, constrained networks, including, like I said earlier, BACnet, NFC, Bluetooth, a number of them. We see that there is this new generation called low power wide area, which are so strict that they can't really fit in the same class as 6LowPan. And so we could not reuse the techniques that are developed for all those technologies. So we formed a different working group. Different crowd attending, different RFCs being produced, we formed a different RFC. At some point, you can't fill everything into 6Low saying it's low power. There is kind of a class that you can serve with a certain sort of protocol. And then you have to define something radically different. We form a new working group. So it's mostly IP over foo. It's also the maintenance of 6LowPan. So 6man, I went through it. It's maintaining everything that all the stack of RFCs that we've done in the past. And more interestingly, it's also turning all this history and this knowledge that we built across all those RFCs into internet standards. And we have Bob in the room here who is highly responsible for that. So basically, we have 802.200, and now we will have all the rest of the core family of IPv6, I guess, turning into internet standards. And that's 6man doing it. So 6TiSCH is this that I mentioned before, this working group where we try to build an architecture for IoT. Which RFC would you use? How do they combine together? What is the role? What is the complete stack? It is defined to operate just like 6LowPan was designed to operate over a particular MAC. In this case, it's 802.15.4 TSCH, meaning time-slotted channel hopping. Time-slotted channel hopping is very interesting because at the MAC layer, it's quote-unquote deterministic, meaning that you basically cut your radio in frequencies and time, and you allocate a cell in that matrix to a particular transmission. So you actually build a schedule, just like your 3GPP will build a schedule where you have a particular resource block. And so 15.4 allows you to do that. And what 6TiSCH does is build this stack of IoT protocols over this particular MAC. So there were some components which were needed at the intersection of layer 3 and layer 2, which we built in 6TiSCH. And we'll probably push them to IEEE because they kind of belong to lower layer. At the time, 15.4 did not really have an LLC. So this thin layer, which is above the MAC under IP, which readapts to this particular MAC. There was nothing for 15.4 at the IEEE. We needed that to build this 6-dish stack. So we defined one. And now, as it goes, the IEEE took interest and they form 802.15.12. And my hope is that 15.12 will actually be the place where the maintenance of our work will happen. Nevertheless, 6-dish is mostly done for at least its current goals. And we are completing our round of RFCs. I don't know if we'll reach charter. Probably it's going to be a different effort for deterministic flows. And I'm trying to steer that. 6-dish did non-deterministic IP, so best effort, if you like, statistical max IP over a deterministic MAC, where you schedule. The next generation would schedule at both layers, so you can really know deterministically what goes where. And now you can do more strict protocols like control loops in industrial, things like that. 6-dish is still traditional IP over this MAC. So you can take a 6-dish stack, put it on a different MAC layer. Guess what? AX is now producing those OFDMA, which can actually map the time slots in 6-dish. So if you take what AX calls a tick up, it would be a slot, a time slot. And if you use these OFDMA subchannels, you can actually map them to 6-dish channels, channel offset, as we call them. The result of that is whatever we design in 6-dish for 15.4 could actually be ported on Wi-Fi in the new AX generation. Actually, I will be talking to Wi-Fi next week about that. So that, we do it, like I said, for one particular MAC. 6LoWPAN was done for one particular MAC, but the goal is to be able to port it on different MACs and get the same result automatically, kind of. DHC, I mean, who knows about DHCP? I guess everybody has heard about DHCP. It's hard to work on IP without ever hearing about DHCP. So it's been there for like 30 years.
27 years.
Yeah, so incredible. So still tasks for doing work, because the more you want to provision through DHCP, well, the working group keeps providing that. So DHCP is still very much alive. Distributed mobility management. So this inherits from generations of work starting at mobile IP. So mobile IP had this concept of a home agent, which made it so that a particular mobile router would build a tunnel to where it should be, which is his home. And the packets from the internet would theoretically go to where it should be, and then tunnel from this home to where you are. That's mobile IP in a nutshell. Now the problem was this anchor, this local anchor, which was your home agent. With DMM, we can distribute it. So it's like when you're roaming with your phone, you're capable now of attaching where you are and build a local tunnel as opposed to a global tunnel back home. So DMM is still very much alive. It's been there for a while because it inherits from work which we did in the early 2000s. So this is the continuation of NIMO, of, what was the, yeah, MIP6, well, MIP6, then NIMO, then, what was this? PMIP also. NetX, which just completed. Well, so it's a continuation of working group. Sometimes you reach out to a working group. Sometimes you say, oh, this is redone, but there is a continuation to be made, like 6LoW was really not 6LoWPAN because there was no WPAN, but we still have work to do. So DMM is taking this to distribute the home agent, kind of, the anchor. So DNSSD is the continuation of MDNS Bonjour to basically enable to discover something, a service, but not limited now to a local network, a layer 2 network, a broadcast domain. The capability to actually look at beyond your broadcast domain. So that has a huge number of very interesting use cases as soon as your network grows. Like you want to be able to discover, I don't know, a video or something, but it's not on your local subnet. Today you're screwed. You can't find a printer which is not on your local subnet. So Deprive. Deprive is about securing DNS. I don't know much about it, so if you want to say something about Deprive, but I'm not intending it.
Yeah, so Suresh Krishnan. So I'm the Internet AD, like responsible for some of the groups there. And so this is like pretty much for providing confidentiality for like your DNS queries, because like the DNS queries like leak a lot of information, and the idea is to minimize the information exposure due to DNS queries. So that's what this working group is trying to do.
Thank you, Suresh. HIP has been there forever. I'm surprised it's still there. So it's all about separating the naming the identity piece of an IP address and the localization piece of the IP address. So now you have two addresses, one which says where you are and one which says who you are. The interesting thing is when you talk HIP, the upper stack says who to who, doesn't really care where. Now, if the people are moving, actually there is a mapping in the HIP layer somewhere under the transport, which maps this who to who into a where to where. That's how the packets gets to where I am to where you are. So you can move, I can move, they can move separately. And each time the mapping is updated, so basically the discussion can continue. So it's a variation of MIP without a anchor, kind of. Interesting model, but it's like MIP. I've not seen that it's deployed anywhere, so I'm still surprised it's still there. But it's still there, okay, live and kicking. HomeNet. So HomeNet formed to enable multi-subnet home networks. So it's kind of a complex technology. It's more complex than my own home, right? I still have a single subnet at home. I have IPv6 thanks to my service provider in France. I still don't have multi-subnet at home. I mean, it's really kind of a vision. And why I don't have IP subnet? Or do I have IP subnet? Maybe because I would have to configure that, set them up. And I don't want to go ahead and do that. And then when I move my TV or my laptop from a room to another, I have to renumber my laptop. I know, nah. Right? I'm not doing that. Now with HomeNet, all those would be behind the scenes. So you would benefit from the broadcast domain isolation, a number of things that you will get from routing, like security isolation. You can have your IoT prefix because you don't trust the devices, have some rules between network and another if you like to. But it will all be automated. So one of the protocols that HomeNet has done is how do I go ahead and discover my routers and assign them prefixes so you actually automatically subnet your network. So your service provider would give you, I don't know, /48, and HomeNet would automatically configure all your routers with /64 and route between them, etc. So you get the magic of layer 2. It all works with the benefits of layer 3. So it's defined in the context of home. Some of the protocols could apply beyond that in Campus or whatever. But start low, just like I said, 6LoWPAN started on 15.4, HomeNet starts at home. Thread started at home. IP-Wave, that's one of the newcomers. So IP-Wave is about vehicles. And you see, if you follow what's happening in cars and IoT, you will see that the next generation of cars are going IP. There is a huge IP and Ethernet. There is huge work at IEEE about Ethernet on 2 wires, and so at least 10 megabits to start with, but they want to go into the gigs soon. And IP at the same time. Why? Because by multiplexing at the IP layer, you will save wires. You will be able to use wireless if you want to at some points. And if you save wires, you save cost, you save building. I mean, if you see the shape of the wiring in a car, it's completely awful. So having faster fat links and some switches inside the car will save you weight, that's gas, will save you maintenance, that's less wires that can break or unplug. So there's a huge benefit for cars in going IP and Ethernet, and they're all going very, very quickly to that. So that's one angle of IP there. IP-Wave is more about the vehicle to infrastructure, vehicle to environment. So for instance, there is this 802.11p, which is a new variation of 802.11, which allows you to connect as you go. Well, the model for IPv6, neighbor discovery, etc., is not at all meant for that. So right now, IP-Wave is in the prime statement phase, but clearly you cannot use the traditional link model, neighbor discovery broadcast model, of IPv6 in that environment. So if we really want to bring IP in the vehicle-to-vehicle or vehicle-to infrastructure, we will have to design something novel in that group. So I'm really interested in seeing what's going on there. And the other newcomer is LP1, low power wide area networks. Have you heard about Sigfox, Laura? Raise hand. Okay, so I love this technology. So they really have a paradigm which is so counterintuitive that I really love it. We are used to making networks faster and faster, more and more reliable. Those things go completely the other way. They are slower and slower and less reliable. Don't expect to have 80% of your packets through. It's just, you send some meter, send some information and praise that it gets there. It's more often than not, it does, but you can't build anything which would depend on it. On the other hand, you can spread your sensor on square miles. With just 1 or 2 gateways, you can serve already a large area. So it's really meant to have a very cheap deployment of meters, which will measure hygrometry, which will measure temperature, seismic variations on a dead volcano. I don't know, something which is not critical, but has to be deployed on a wide area at a low cost. And you may have to serve tens of thousands of sensors, which don't speak very often. So it's interesting because it's a hub and spoke model compared to the traditional 15.4, which does mesh. Meshing means complexity, means engineering, which means cost. With that, you can really have a high throughput, high quality network. But those are completely taking the opposite way. Let's do a simple hub and spoke. I'm placing this quote unquote IP here, and I cover miles and miles. So this opens to very new and interesting IoT use cases. So we are defining IP compression, we are defining fragmentation. The MTU on a LoRa network in the US is 11 bytes. Do IP over that? Well, we do, but we had to take certain measures.
Pascal, on the slide before, are we still working on IPv4? Really?
Some people are asking to provide an IPv4 version of what we did for IPv6. Now, to be honest, the chic as it is doesn't need to be changed at all. It's just a matter of rules. So we can support IPv4 with it. I don't think we need any change in it to support IPv4. But yes, if people need IPv4, it's not like, should we say no? I mean, it's a question. I mean, this is for rechartering, right? We have not rechartered for that, but it will happen. Some people the question will happen. We will ask around if we are interested in working in IPv4. To be honest, what you need is a 2-pager saying, hey, yes, it can be done. Do it.
Yeah, Suresh Krishnan. So one thing like I kind of push back is like on v4 only work. So one of the things that came up like in the IP wave before was like, should we do a v4 mapping? And I pushed back on it a bit, okay? So if something gets done and it works well with v4, like I'm not gonna push back on it, right? Like, but if somebody says like, hey, I'm gonna do this IPv4 only thing, it's probably not gonna like pass muster, especially at this point where we worked very hard to get like v6 everywhere and like, done the IAB statement on this. And like, so we are kind of really trying to keep the v6 train going, right? And so it's very unlikely that like something that's v4 only work, that's new work is going to get chartered at this point. But like, there's like stuff we need to maintain. IPv4 is like just as IP as IPv6. So we're not going to shirk our responsibilities to maintain like the things that are out there. So like we will be continuing to do IPv4 related work. So if that's your question, but it's very unlikely that IPv4 only work is going to get chartered, at least in this area. Like I know like in art, right? Like people are doing stuff like that, right? And I kind of push back on the ESG when it gets to me, but it's kind of really case by case basis really. But the general idea, like no, v4 only work starting off.
Yes, and as I said, to compress IPv6 in 11 bytes or something, we had to take very strict measures. And one of them is you don't really see the IP header at all in the air, which means that probably the same device sending the exact same bytes could be uncompressed into v4 or v6. because it's completely stateful on the network side. So this basically the only thing that turns could be that the up limit or something like that, and even usually we make it a constant. But those can be mapped in V4 and V6. Most of the other fields are kind of constant, and then there is an enumeration to say what your IP address is in the table. Well, if this table says V4, it's going to be V4, right? So I tend to think, and I have to make the exercise because I didn't make it, but considering the protocol as it is, I tend to think that just by changing the rules of compression, decompression, without changing anything in the device, we could generate IPv4 or IPv6 packets. But it still would be co-op at UDP, but it could be V4 or V6. And probably the device would not even know or care. It's just a matter of what the upper layer, the rest of the network wants. So INTA, like I said, this is another work group that's here to stay because it's really associated to the area itself. It's everything that doesn't really fit in a particular working group, but is still of interest for the area at large. LWIG is an implementer. So I should have mentioned it in my examples of interesting working groups because this is yet another type of working group. It's more like implementers talk to implementers. Let's give not deployment best practice like in V6 apps, but more implementation best practice. And you will find drafts which say, hey, you could do it this way. It doesn't take any change in the protocol RFC, but if you do it this way, it's going to work much better. It's going to be much simpler to implement. You have this trick. If you do your cryptography this way, oh, you can reuse, I don't know, the Edwards curve and well, anyway, you can reuse different curves by just tweaking this and that saves you code. You have so little space for your code. Here is a trick. So all this happens at LWIG.
Yeah, so just adding to that, there's also stuff in here where we define like different classes of devices. So when we talk about different categories of constrained devices, that's where we did the definition. So like, some devices have like, 10 kilobytes of memory, for example. Some of them have like 100 kilobytes. We think of them all as constrained, but there's different classes of constrained devices, and that's where we kind of define those things. And there's also like some cool work going on right now, which is, for example, like TCP, right? So how do you do TCP on constrained devices? Like, how do you set the timers and those kind of things? So it's like really hardcore implementation stuff. So if you're really interested in implementation of like the low power and the constrained device stuff, like you should like really end up there.
NTP, well, I guess you have time on your phone, and it's thanks to NTP. So NTP v4 now is the standard for getting time across a wide area. It won't be as precise as 1588 defined by IEEE, because 1588 will be just on a single Ethernet, and then 1588 itself has to be profiled based on the use case, how many repeaters you have, are you doing a smart grid network or what. Here it's generic for the whole internet, meaning that obviously you can't get to the very precise results you could get with a particular profile of 1588. But still, you get a very reasonable sense of time, like 200 milliseconds across the internet. So if your iPhone has time, if most of your network after your PC has time, usually it's because you have NTP v4 behind the scene. Software, it's kind of old now, right? It's tunneling V6 over V4, for instance, or V4 over V6. So for instance, if your core network now has migrated to V6 and you still have end-to-end V4 connections, you can think about defining this logical wire for transporting V4. It's kind of a tunneling mechanism, you could say. TikTok is studying the new way we can do timing and exchange time. I've followed it only scarcely. I don't have much to say about it. It's about time. And this is not a working group. So we are done through the working groups, but there's also this kind of cross-working group effort. People from different working groups actually contribute to the Internet Area Directorate. It's kind of Suresh secret helpers.
Yeah, so there's like people who've been like chairs before. They authored a lot of documents, so we kind of use them to review documents. So let's say a working group is ready to publish set of documents. So what me and Terry, who's my co-AD, what we do is like we kind of push a button to get an indirected review. So before it leaves the working group. So what happens is the experts who are kind of outsiders to the working group itself, right? Because they don't know the exact technologies of the working group, but they're like well versed in internet area ideas, which is like they know IP very well, they know like DNS, DHCP, those kind of things very well. So whatever I put in at the end of the list as like reading, required reading kind of thing. So they're like very good at it. So the idea is to find out issues pretty early before it goes to the whole IETF. Okay, so we kind of try to do like a multiple step of process. So like people get an early review of the document with fresh eyes outside the working group, but like really before it goes to the whole IETF. So that's kind of the thing. And one of the things like we kind of also use it for is to like, when there's like new people coming into the IETF, we kind of ship them off to like somebody at the directorate who will help them out, getting to learn the groups and everything. And also kind of like succession planning. So like, whenever like somebody is in AD, like they're there for 2 years or 4 years or 6 years, whatever it is. The idea is to find like a pool of participants like from there who will also take on like leadership responsibilities in the future. So like, for example, like Pascal, like, is like doing stuff there. So like the idea is like when we want to do this overview, like I want somebody from there to do it. So they get like experience to do stuff in the future. So I did this like, 3 years ago, the same tutorial in Japan. So I became AD at some point after that, right? But the idea is to like get people to know more about the area. So there'll be like a succession pool of management too. That's like kind of the ultimate like choice as well.
So usually you'll find directorate associated to each area. There is an interesting one which is not vertical per area, but that's horizontal. It's the IoT directorate. So for IoT specifically, we have formed directorate, which is not limited or specialized in one particular area. And then just because we are like a layer, if you remember my matrix at the very beginning of the presentation, I had the 3 layers with 3 areas. We had internet, we had transport, and we had application. But on the side, we also had maintenance, security, and routing. Well, if you look at it, these are the interface of our area. We have to talk to those 4 areas, transport above us, but mostly routing on the left and security and operation on the right. So that's why they're listed there. These are our interface. We need ops to configure us and to give us back feedback on how our protocols work in the real world. We need routing, and routing needs us because there is an interaction between what's happening on the link layer and how the routing can abstract it and present it to the rest of the world. And obviously now the IETF has this role that anything that you send us at the IETF must be secured. So more often than not, before you even go to all the other areas for the final review of your work, you asked some review from the security area. If there is some sensitivity in what you're doing to security, then we get help from the security directorate before we even go to ask review from other directorates. So everything now has to be safe that we produce at the IETF. And that's why you will find this section at the end of each RFC we produce, which is the security consideration. You have to write a security consideration. You have to analyze how which threat can apply, specific threat apply to your new protocol. You have to provide information on how you think they can be defeated or avoided. And the security security directorate will actually review your work and say, oh, there is a big hole, or it's okay. We are starting to see more and more management sections as well. It's not yet mandatory, but it's kind of cool when you provide a new protocol to say how you think it's going to be managed. Right now, you often find a companion document with the Young model, for instance, that comes with it. Some pointers on RFCs, good to read. So some of them are recent, like you mentioned the 8200. MIPv4 happened after MIPv6, which is kind of interesting. But this is the second version of MIPv6. The first one was 3775. And here are all these interesting links. So if you try this link, the data tracker, you will see it's gotten very friendly. I really love the new data tracker that we have at the IETF. It's kind of the IEEE mentor, but it's really easy to navigate. You can see the working groups, you can see the areas, and if you click on the working group, you can see which documents are being are drafts. I need to go through a little bit what a draft is, and then which are RFCs. So the cycle, basically, if you have not seen it before, is that you can publish any document you like, but you publish it with your name. It's going to be called draft Doe, draft John Doe. If you want to publish it to a particular working group, it's going to be draft John Doe working group, and then whatever you like, -00, because it's the first generation. And now if you publish new variation of it, you have to do +1 every time. So the drafts are sequenced. They start with draft, name, working group, whatever words qualify your work, sequence number. And you publish that. At some point, the working group may like it, and we'll call it draft IETF instead of your name. You give token to the IETF. The work doesn't belong to you anymore. It belongs to the working group. Draft IETF, working group name, whatever qualifies, it starts at 0 again. Goes through the process, ends up RFC. So it may be a standard track if you're doing some standard work, could be informational. If it's standard track, then you have initially, well, it used to be 3 levels, now it's only 2. You have the normal standard track, and then you have the internet standard, which is really like the golden IPv6 8200. So in the working group page, you will see the drafts that are being processed, and if you scroll down, you will see the RFCs that have been produced. You can also see for a given working group, everybody who is responsible. So you will find the mail archives. You just click there and you can register to the mail. You will receive it. There is no fee to pay, nothing. You just register to it and get the mail, and you can talk about it. And there is the jabber, the room for during the meetings. And that's pretty much it. And I think we are out of time, but any questions? And then remember, 15 minutes from now, there is the meet and greet. No, this is one question.
Good afternoon. Saulo from the International Civil Aviation Organization. Just one question about the IP wave. When you talk about vehicular environments, which type of vehicle environment you are talking about? Just ground, low speed, or this involves other environments as well?
So this is like pretty much 802.11 OCB. Like that's the only thing that we are chartered for right now. So it's right now vehicle to vehicle and vehicle to infrastructure. Like so. Pretty much cars and trucks and platooning and adaptive cruise control, those kind of things are the only things we are like. So it's not like a lot of the safety stuff is not in scope really, right? Like so, as I said, like once the working group finishes the deliverables, we can recharter to do more. But right now, that's the scope. It's very tightly scoped right now.
Any chance to include aircraft on that?
So there's been like stuff that's happening before. There's like a lot of attempts to do like aircraft stuff. I remember like connection by Boeing. I don't know if you know about it. Like, so we talked about it, like that is generally in INTA. So it does I never seen a proposal that's clear enough to charter. But if you do have some proposal that's like clear to do, because one of the things like I'm kind of pushing back on is like very boil the ocean kind of proposals, which have a lot of things to do. So I kind of want something to be really scoped down. So if you really have something you want to bring up, come talk to me. We can talk about a BOF proposal coming up soon, and then we can go from there.
Okay, I'll talk to you later.
Thanks.
Thank you.
And that's it. Thank you for being there, and I hope we meet again up there in the meet and greet. Voila. And yes, we have a wiki which will tell you, for instance, how you can come here. Well, it's too late. But it's very useful, for instance, if you have any direction, anything, the wiki is a great resource. Many thanks again. And there we go. You're free to go enjoy the food up there. Immédiat.